All right, for those that are online, can you hear and see the screen okay? Okay, great, thanks. Okay, so make sure you guys can see the screen okay too. All right, so last time, what did we talk about? Anybody want to do a summary?
Well, last time we started off by discussing the difference between a regular average and the root mean square and why it's
Okay.
important when working with ECE. Then we started introducing the idea of complex power and the different terms and meanings that come along with that.
Correct. And RMS. Complex power. Okay. So one part of the average power and the RMS one that I wanted to go over was that in this RMS, root mean square, again, anybody want to take a stab at defining what that means in your own words? Yes.
It's just a different way of taking the average so that you can have like an actually usable average for when you're working with alternating currents and whatnot. Because let's say you have a sinusoidal wave, taking the regular like arithmetic average, or like what we normally think of as the mean, that would just get you zero. But we know we can still get power out of that. So taking the root mean the root mean square or the RMS average sort of lets you still get like a term of power. It's how much current an equivalent DC current voltage would need to have the same power output.
Correct. Thank you. So yes, it's a way of giving you, RMS gives you, instead of an average value, which if you were in a sinusoid would be 0, it gives you a number. So you can quantify and get a number for relating it to DC power. And so that number, instead of being 0, will be a positive number because you're squaring all of the negatives. And so it will give you a value that you can then compare to other values and say like, oh, if it's 5 watts or 5, the other terms, VAR or volt ampere reactive is the reactive side of it, so the imaginary side of it. Those values will be a value that will give you some quantitative information. So instead of 0, yes, it gives you a value. So in this, we're going to see a lot of these RMS values. So again, it's taking the square root of the average and squaring the signal. So if we have any signal, I just called it X to quantify. It could be voltage, it could be current. And it's of a cosine form with a phase shift. And we take the square of that. Note that, sorry. Okay. Note that we're going to have XM, which is going to be the amplitude of the signal, and that's going to be a constant. So in the integration, we take that part out. So we get XM comes out to the front, XM squared, and T, again, is also a value. So that's your time period. So those are constants that come out, and then we have the cosine squared omega T plus the phase shift. Note that a cosine squared also has this property where it's a half 1 plus cosine 2 omega T plus 2 times the phase shift. So with that, we can actually rewrite this. No, that's not what I meant to do. No, that's not going to be good. Okay, I'm just going to rewrite this whole thing. So we have the square root of XM squared over T, 0 to T, and now it's 1/2 plus 1/2 cosine 2 omega T plus 2 theta V dt. So now when we take this,
Could I just pull out the 1/2 constant?
mm-hmm. So now we have, the half is just going to be xm squared over t, and then we can kind of split this integration too. So this can be 1/2 pulled out, 0 to t of dt, plus and when we integrate this, theta b, the 2 omega, what does this integrate to? Anybody remember?
It would be 2 omega sine of 2 omega t plus 2.
Actually, it just goes to 0.
Oh.
We're integrating over the period, that's why, right?
Yep, because we're integrating over one period. So if you remember, you integrate over it, and the top and the bottom actually cancel out. So you get 0,
That's fair.
which is really nice. So all you have here is the xm squared over 2t, and then this becomes t evaluated at 0 to t, which then becomes xm squared 2t times t so this is the average, or sorry, RMS, not average, RMS value for this of any quantity that has a sinusoid in it. So we can just write this as xm over the square root of 2. So this makes it really nice that we can always just say, if we have a sinusoid in there, all we need to do is take this, that number, the amplitude, over the square root of 2. So this is very nice. So wall voltage, when we talk about the RMS of that, it's 210 volts or whatever it is. And then you take the RMS would just be 210 over the square root of 2. Yes.
I remember when we were taking notes yesterday and talking about how relating these things together, we also included some term of like e to the power of j and then the phase shift of the thing. Is that going to be involved in this, or is that just incorrect now?
So this is the RMS value. Let's go back to 14 with those notes. That wasn't that right. Spring, there we go. Okay. So I see what you're, okay, so that's kind of getting back into this. So we can rewrite, so V RMS is how do I say this? So remember back to phasors. I think I had. So you can rewrite, for a phasor, you can take the amplitude. This doesn't have a very good description, but So 6 cosine omega t, if you were to change that to, that's the time domain of it. And if you remember from the phasors, you would take the 6 and write it as 6EJ 105 degrees. So you take the phase shift. So it's the phase shift, and then you use the omega to find the actual value at that one omega only for the L and the C. So that would be, for the C, it's 1 over 1 over j omega C. And then for the L, it's j omega L. And you use just that one omega. So that gives you at one frequency what the value of the impedances will be. So that's only useful for one value of omega. And we usually want to know, well, what about the range of omegas? And how do we solve if we don't know our exact value for omega? Yes?
Those graphs, I guess you would call them, do we have access to those? Or
So these are from the book. They're figure, I didn't write this one, but it's right around figure between 7.2 and 7-7. These are on the notes for, I just uploaded new notes yesterday for 15, lecture 15. If you also, they're on there too.
that's not going to be in the learning materials for Unit 3?
I may not have put them there, yeah. Yeah, so they'd be under the lecture notes instead of the learning materials. So that's when you're talking about one omega. So for VRMS, we can utilize that result to also write it in two different ways. If we're looking at just the magnitude, it would be just the magnitude VM over the square root of 2. And if we want to include the phase shift, it would be that E raised to the J theta V. So this would give us the polar form of it. And so we can write VRMS and IRMS in those terms, and then the complex power is going to be the VRMS times the complex conjugate of that IRMS. And then we have apparent power. Do you guys remember what unit you use for complex power? Volt ampere, VA. Again, these all mean watts. All mean power. They're just different terminology for them. So volt ampere is still watts. It's just meaning that it's complex. So that's how they denote that there's a complex component to it, is with volt ampere. So when you see if you see watts, you're thinking, oh, that's the real part of the component. And if you see volt ampere, you know that there's complex portion to it. For the real portion of that, so that is also going to be done in, this is going to be your polar form. And then the magnitude of it is going to be the apparent power. Rectangular form is going to tell you the real portion, which is going to be in watts, and then also that imaginary portion, which is called reactive power. So a new term again, reactive power, and that one is going to be VAR, volt ampere reactive. Volt ampere again reflects that it's imaginary, and then R is the reactive portion of it. So VAR is for the imaginary portion of that one. Okay, so what I want you to take away from this is that, okay, now we want to find complex power. We want to convert it into the RMS values for the voltage and the current. From there, we can find apparent power by finding the magnitude in polar form. Change it to rectangular form, we can get real power, or the real power or power absorbed in watts, and then the imaginary reactive power in volt ampere reactive. Okay? Then the last part of this is called the power factor. What the power factor does is tell you if you have a leading or lagging relationship for a load. And so if you're purely resistive, then your PF factor is 1. So that gives you like, okay, there's no imaginary portion, there's no reactive portion. So it's just resistors in there. Or it has components that are canceling each other out in there so that it looks resistive. It's going to be exactly in phase with your current, and your voltage will be in phase with each other. If this power factor is inductive, then their current will lag your voltage, and it will be considered lagging. If it's equal, it will also be lagging. If it's leading, then you'll have a negative IZ. And if it's equal to minus 90, it will be leading. Okay, so let's calculate these actual values. So we want to determine the complex power, apparent power, average power absorbed, reactive power, and power factor, and include whether it's leading or lagging. So we're going to start with the first one. What would be our first step that we would want to do? Do what?
Converted to polar form?
Okay, so we're going to convert it to RMS form, which is the polar form. So the V RMS will be what?
110
To the minus 60J.
minus the 60 degrees
Is it
doesn't
over?
do anything.
Sorry, what?
Is it over root 2?
And then you do it over root 2, correct?
Wouldn't it be 110, not just?
Yeah, I don't know where I got 100, sorry. 110 minus 60J, and then the IRMS will be
4e to the negative 60. Or is it negative 25?
negative 25.
I don't know which of the two I'm supposed to.
Yeah, so you ignore the omega.
Okay. Over root 2.
Yes. Okay, and then, so then S is going to be VRMS times the complex conjugate of IRMS. So you take 110 over square root of 2, and then multiply it by 4 over the square root of 2, e to the plus 25j. And the magnitude of that is going to be 4 times 110 over 2. So 220. And what was the units for S?
It's not watts.
Not watts. Volt ampere. So that will be your S.
Why is it just 220 and not like something these?
440 divided by 2.
Okay,
But instead of what?
So we're taking the absolute value, right?
So it's the magnitude
Okay.
of
so
the
we're just
polar.
focusing
On the
the
magnitude.
leading coefficient. Okay.
Yeah, so that, I think it's called the radius. Is it the radius? The R, RE to the J theta. So
Mhm.
that R. I can't find the value here.
What happens to the to the whatever, yeah.
818. So remember, magnitude is just the number. So it's just R. The magnitude is just R. Sorry. So the magnitude is equal to just R value. So in this case, it will just be the magnitude in front. So it's not the absolute value, it's the magnitude. Because we're talking about a complex number. Because it's polar, yeah. So this is polar form, and then we're taking the magnitude of that, which is just the 110 times 4 over square root of 2 squared. Does that make sense? Okay, so
And
then,
apparent power that we just found?
yep, so this is the apparent power. Apparent power. And now we can find the real and the imaginary portion. So how do we convert this? So we want S in rectangular form. So how do we?
Okay, I found this on the web for what read S in rectangular
Stop.
form. Check it out.
There we go. Okay. So how do we change it to rectangular form?
It's straight, right?
So from polar, you take R cosine of theta plus R sine of theta J. And that's how you get to rectangular form. So going back to this, we have 220 e to the j, or minus 35? Yeah, 35 degrees. And so S will be
220 cosine of negative 35 plus 220 sine of negative 35J.
Yep. And then we call this portion the real, P average. And this portion will be the Q, which is the imaginary. So P average ends up being 180.2. And Q is minus 126.2. So units.
What is RAB?
VAR,
Yeah.
volt ampere reactive, and then P averages. You guys remember?
Watts.
Watts,
So
correct.
it's real. So it gets to watts.
Yes, watts. Woo. Oops. Okay, so these are watts. So this is the average power absorbed. Oops, average power absorbed. And this is the reactive power. Okay, so now we just need the power factor. So the power factor is found easier after you've found those two by just taking the absorbed power over the magnitude. So 180.2 over 220.819.
What does PS stand for again?
Power factor.
Power factor. Uh-huh.
Because that's.
And then you're going to look at the angles, and you can see that theta z So you're gonna take this for the power factor. So it's the voltage compared to the current, and in this case, the voltage was minus 60. And the theta is, the current was a minus 20, I think. Minus 25. So that minus 35 degrees, or I guess it's up here, is where you can see what it is, and if it's negative, it's leading, and if it's positive, it's lagging. So in this case, it's negative, so it's leading.
So does that mean that a power factor has like a magnitude and like whether it's leading or lagging?
Yeah. Yep. So you just have to look at the complex power value of angle there.
Okay.
And that will tell you if it's leading or lagging. Okay. You guys ready to do part B?
As well.
One other thing for these, this is just another way of writing that EJ. So remember that's considered called the angle. This thing is called the angle. And you can just, it's rewritten as EJ to the 50 degrees. So just remember that's just another notation and way of writing that. So we'll do B, and then I'll give you the answers for the rest of them to give you guys practice to work on them. So go ahead and work on B to find same things, the complex power, apparent power, average power, reactive power, and power factor. right. Okay, so BRMS 12 over square root of 2, EJ 30, and then IRMS is 0.4 over square root of 2, EJ to the minus 15 degrees. And then you take the complex conjugate of that one, so it becomes 30 plus 15 to give you 2.4 EJ to the 45 degrees. So then the apparent power is going to be the magnitude of that, which is 2.4. Again, that's volt ampere to signify it's complex. And then the rectangular form is 2.4 cosine 45 degrees plus 2.4 cosine 45 degrees J. That ends up being 1.7 for both of those. And so watts is the units for the P average, and then VAR, volt ampere reactive, for the Q. And then for the for the power factor, you look back to the complex polar form, you see it's positive for 45, so that's lagging. And then 1.7 over 2.4 gives you
0.7.
yeah, and I don't know where I got the other one, but it is 0.7. Okay. I think it's 0.71. Was it 0.
Well, it could be 0.71.
Okay.
Well, it could be 0.7. Yeah.
Okay, I think, yeah. Okay, questions on this? Okay, so just be able to understand, what do those terms mean? How do I calculate them? So this is what I want you to take away from this complex power. Okay. All right, the next kind of topic that you're going to need to, so in the notes, I'll have the solutions for C, D, E, and F if you want more practice on those. And then you're going to do that also for your homework. So just note that that's one of your next homeworks is going to be calculating these values. Okay, the other next portion is called maximum power transfer. So a lot of times when we have a complex circuit, we want to create a Thevenin of that to make it simple. Note that we can do a complex Thevenin, which just means that we have impedances in there that are either inductors or capacitors also in there. So those would be considered an active circuit when they have those capacitors or inductors in there. So the RS could actually be a ZS, meaning that it has complex components in them. And so we want to know, like when we put on a load circuit, what is going to get us the maximum power transfer from that circuit to the load? And so, do you guys remember how to find the maximum? First off, how would we write this in terms of IL? I'm just going to do it with R's first.
VS divided by RS plus RL.
Correct. And so our power is then going to be VS squared RL over RS plus RL. So remember, when you take a derivative and set it equal to 0, that gives you a maximum or minimum, right? So,
I have a question.
yes.
So are we substituting our equation for IL into that power equation?
Yeah.
Should the bottom be squared?
So this portion's squared.
Yes.
Yes, thank you. Sorry. Yes, so that portion is squared too. So yes, you have the RS plus RL squared. Okay, so if I was to take, the derivative of this with respect to RL, I would then have RS plus RL for the bottom, and then it would be, wait, minus, oh, okay. I would rewrite this, VS squared RL, and this would be minus 2. So then I would have to take the derivative at the first, the top, and then the derivative at the bottom. So anyway, I end up with VS squared 1 over RS plus RL squared, because I take the, this would be the first, where is my pen? This portion. So I take that portion, and then I have to take the derivative of the second portion. Maybe I'll just rewrite it here. So I'm going to take this first portion, and then I need to take, do it in green. So I take the derivative of this one, and then that is just the VS squared RS plus RL to the negative 2. And then I take the derivative of this. And so that ends up being a minus 2 RS plus RL, and then minus 3. VS squared times RL. And then I take the derivative of the inside, which is just 1. The RS plus RL, that will just be a 1. So rewriting this is rewritten as this. So minus 2 RL, the VS squared goes out, and then I have the RS plus RL 3, or RL cubed on the bottom. So I set that equal to 0. How do I get that equal to 0?
Inside, it's gonna have to equal each other.
So RS and RL will have to equal each other, right? Or negative of each other.
If they were,
Wouldn't that make it undefined?
yeah, that would
Yeah.
be
So
that
like
would
the
just
two
divide the denominator by
fractions will have to
0.
equal each other.
Yeah, so,
So that gives us,
so R2L, well, 2RL would have to be equal to 1.
No, because there's a cube on the bottom, so.
Oh, yeah.
RS plus RL squared.
So when you get a common denominator there,
okay.
so common denominator, this gives you denominator. So you have RS plus RL on the top for that one, minus 2RL. And then the bottom all goes over to the 0, so that equals 0. Okay? And then solving that, you end up with RS minus RL equals 0, so RS will equal RL.
Okay, yeah, that makes sense.
Okay? You guys follow those?
Yeah.
Okay. So this is when there are R's. If they're Z's, it's going to be the same thing. So with Z's, the complex power, you use V. This is kind of written weird, but V times the, I'll just, VRMS times the complex conjugate of IRMS. That's easier to do. And then that gives you the square root of 2 times the square root of 2 on the bottom, so that's where the 1/2 comes from. And then V in this case is your Z times I. And so it ends up being I squared RMS R and I squared RMS X, where X is your J component.
Can you run the last part one more time?
What?
Can you run the complex part again? I'm not sure I followed.
Let me just skip down to this part. This is going to be easier, I think, to follow. Okay, so IL is just VS over the summation, so the same idea. And then you take, so we're looking at the average power, so you take the average power portion of it, and then you take the partial of the average power over respect to RL equal to 0. And then this is where it gets really messy. So just trust that the math is correct. So you take it with respect to XL and you set it equal to 0. That means this will go over to the other side, and this will go, multiply over to the other side.
Wait, what's XL?
Oh, wait. Sorry, this is the wrong one. This is the average, 1/2. Do this again. This is RL. And so this ends up giving you the RS squared, or RL squared plus XS plus XL squared minus 2RL RS plus RL equals 0. So solving this gives RL equal to RS, so the same result. Oops. The same result as we had before with just the real values. And then when we take the partial average with respect to XL, set that equal to 0. This will cancel out, the bottom will cancel out, and we just see that, and then the minus 2 will go over. So XS is going to just equal a minus XL. So the maximum power transfer, RL will equal RS, and then your imaginary ZL will equal the complex conjugate of the ZS. And then the average power max will be 1/8 of VS squared over RL.
Is that why impedance matching is so important in certain systems, so they can get the most efficient transfer of power?
Correct. Yep. So this would be the way to get the most efficient power transfer. Okay, so next time we'll go over an example for this max power transfer. And then I'm going to kind of cruise through the material really fast. So on Friday and Wednesday and Friday, I'm going to go over the Fourier. So we're going to skip ahead to the next lectures. And then I'm going to just do examples. So next week, I have some conflicts, so I will not be here in person Monday and Wednesday. So I'm going to do some online examples so you guys can watch the recordings of those. And then on Friday, I'll be back here in person. And then the following week, I'll be gone again, Monday, Wednesday, Friday, and Monday, but I'll be able to do remote lectures for most of those.
Where are you going?
So, I'm taking my daughter on a trip.
Oh, that's fun.
Yeah, we're having it should be fun. All right, see you guys. Do you guys have any, there was a question online, sorry, so Dana. Oh yeah, so no class next Monday, Wednesday in person, there'll be recordings instead.